Good evening, everyone. Welcome to this Edureka session on OpenStack training. Let me start off by briefly introducing myself. My name is Nandan. I currently work as a DevOps engineer in one of the IT firms, and I use OpenStack as part of my day-to-day job responsibilities, job activities, and I've been doing so for the last 4 to 5 years. In today's training session, we are going to take a look at the fundamentals of OpenStack, and we're going to have a basic introduction to OpenStack and try and learn about the internals of OpenStack at a high level. Helps us achieve in terms of IT infrastructure. Okay, so in today's agenda, there is an introduction to OpenStack, the OpenStack architecture, different services or components of OpenStack, and a couple of case studies just to put into perspective how OpenStack is being utilized by, say, in the production scenario by multiple corporates or organizations. So OpenStack is basically a set of tools, or rather software. We could call it a software suite that helps us build cloud computing environments. So if we need to host a cloud computing environment, be it for our internal use or for offering it to the general public, we would use a tool set like OpenStack to build the capability and manage the environment, manage the cloud computing environment. So in order to understand fully what OpenStack helps us achieve, we have to try and compare it with, let's say, traditional computing. So in any kind of organization, be it small, medium, or large, there's always a necessity for compute capacity. So all workloads that organizations run these days run on some sort of computer hardware. So what every organization requires is lots and lots of processing power, lots and lots of storage, lots and lots of devices or equipment that connect those computers together. So we could say that the basis of IT infrastructure is the three components, which are compute, networking, and storage. Based on these three components, our entire IT infrastructure runs. So if we suppose the workload that we are talking about, if we take, for example, a payroll processing system or an attendance monitoring system, these days all of these systems are run electronically, and you need both hardware and software in order to manage them efficiently. And in most cases, the software that is being used is used in a client-server model. So we have, let's say, the main functionality of the software running in a centralized location. We can call it a server, and it is accessed by multiple different clients from, say, connected via a network. So if it is a payroll processing system, maybe some employee wants to check their payslip, etc. They would log in from their browser, from their own computer, and connect with the, let's say, the payroll processing server or the front-end server of the payroll processing system. So in this model, the server always runs centrally and requires a lot of resources to address or to process the requests that are coming in from different clients. And almost all tools, all software which is run electronically runs in this model. So there's always a requirement for processing power, for storage capacity, and network connectivity in any kind of organization, be it small, medium, or large. And the traditional model has been to acquire these resources, say resources like servers, storage boxes, network devices like switches, routers, etc., and then install them locally, that is, install them on our own on-premises data center, and run the equipment as per our necessity, operate the equipment by using the organization's own workforce. So there may be a fleet of administrators working towards only maintaining the servers, maybe a fleet of administrators working towards maintaining the application, and so on. So this has been the traditional IT operational model ever since the computers came into existence, or enterprise computing came into existence, we could say. And this has been gradually shifting towards, say, virtualization, which started almost 10 to 15 years back. And now it is gradually shifting towards the cloud computing model. So we will try and understand cloud computing from this perspective so that we can infer how OpenStack plays into that space. So in the traditional computing model, your logical resource, which you can say a server, which is hosting your application, was tightly coupled with a physical resource, which is, say, an actual server that is installed in the data center. So if we say one web server, it used to mean that it's one physical box installed in the data center. That changed rapidly once virtualization came into existence. And we used to mean virtual machines instead of physical servers when we say a web server or an app server, or whatever logical unit we want to refer to. So the adoption of virtualization led to the decoupling of the hardware from the actual usable resource. So in this case, the actual usable resource is a virtual machine with an operating system and any application software running on top of that operating system. So earlier, the OS used to be directly installed on the physical server, the application installed on top of it. These days, it is, say, a tool called hypervisor, which virtualizes the physical resources that runs on top of the bare metal or the physical server. And it creates multiple virtual machines, which we can say are isolated execution environments. And in these virtual machines, it's possible for us to run different operating systems and different applications, even though they are running on the same physical hardware. So in that model, we can say that the actual logical resource which is consumed by the user or which is consumed by the application is separated from the physical resource. So virtualization helped a lot in consolidating our data centers. So we were able to do more with less, and the advancements in computer hardware technology also helped in that regard. So we could have, say, a single physical server with a very large configuration, about 256 gigabyte or 1 terabytes of RAM, and it's still increasing, and multiple processors in that server, all put into one small casing. So the space that was necessary for us to host hundreds of servers earlier, we could host those same hundreds of servers as virtual machines on top of, let's say, 5 or 10 physical servers. So it helped in consolidating the data center into smaller spaces, save on resources such as real estate, cooling, power, utilities, and so on, and help the organization save a lot on the operating expenses of their IT resources. So virtualization was hugely adopted by a lot of large organizations or small organizations, since it gave us the flexibility in maintaining our IT infrastructure. So the resources required became lesser. Resources like real estate, utilities, and so on became lesser. Number of administrators required to run the data center became lesser. So it saved a lot of expenditure on the company's part into IT infrastructure. So the same capabilities or the same characteristics of virtualization carried over to this new computing model called cloud computing, in which we can say the data center is further operated, or the data center is operated in a consumption model. So in the cloud computing model, we try to offer those resources in a service model. Instead of, let's say, purchasing a product like a server, consumers subscribe to the services which are offered by a cloud service provider. So in the cloud computing model, we can say there are two parties at least involved: the cloud service provider and the end user or the customer or the tenant or the consumer, however you like to refer to it. The preferred term is a tenant. So in a cloud computing environment, the service provider hosts the services, that is your IT resources, and offers them to the tenant in a service model. Hence the term infrastructure as a service, platform as a service, and software as a service. So what we are trying to do here with cloud computing is offer the users the ability to use IT infrastructure without actually investing in the, say, upfront purchase of the infrastructure components like servers, storage, and networking. So in any kind of cloud computing environment, we could break it down to two parties, that is the service provider and the tenant or the customer. The service provider is one who hosts the services. That means they invest in the hardware, they invest in the facilities necessary to provide these resources as a service to the end user. And the consumer pays recurring fee, let's say an hourly fee, to the service provider to utilize these services. So the cloud service provider would host these services by investing in these facilities, the facilities being, let's say, the data centers necessary to host these services. And the service provider will build the capability so that the tenants are able to subscribe to these services using different methods that I'm going to explain to you in a bit, and derive different benefits out of that model. Okay, so to understand cloud computing's benefits, we have to compare it with the traditional infrastructure. These are some of the benefits that we have listed down here. First of all, the benefit of the service model, or providing resources in a service model, is the consumer is able to pay as they consume, pay per use. So you get pay as you go billing model for the consumed services. So say the tenant requires a virtual machine to run their workload. Okay, maybe it's an application that they want to host on the cloud. Then the tenant is able to create that virtual machine and use it until they require, and they would be able to pay for it for as much as they have used. Okay, so there are a few questions. Vipin asks, what is pay-as-you-go model? I will get to it. I'll explain it in just a bit. So pay-as-you-go billing is one of the benefits of the cloud computing model. So as I mentioned previously, in cloud computing, there are two parties involved. One is the service provider and another one is the consumer. So the consumer have requirements. Consumer would have requirements such as running an application, could be a customized application, could be a off-the-shelf application. And to run that application, the consumer would require infrastructure like servers, storage, and so on. So instead of investing in that infrastructure by themselves, the customer would think of availing the services of a cloud service provider. So we haven't got to the OpenStack part yet. Okay, there's another question from Vipin who asks, isn't OpenStack free? So we haven't got to the OpenStack part yet, so just hang on, Vipin. Okay, so the service provider would offer their services to the end customer or the tenant, and the tenant would have a requirement such as hosting an application, and they require the infrastructure. Let's say they require a server with 4 processor cores and 8 GB RAM, and they require 80 GB of storage and so on. So to buy a server, buy a physical server with that specification may cost, say, thousands of dollars upfront. So the customer, even without deriving any benefit from their investment, makes an upfront expenditure just to acquire that hardware, and that hardware needs to be installed in their own facilities like a data center or a server room. Then it needs to be given power to run, it needs to be given cooling so that it operates, functions properly, and you need administrators to set it up so that your application can be hosted on the server. So if, say, a company, if the tenant does not want to invest in that hardware, the other options are to rent the hardware. Again, there will be a lot of interaction with the service provider involved there. Other party who's willing to rent the hardware, there would be a lot of paperwork involved, a lot of other logistics involved. And still they would require a system administrator to set it up, to configure the connections and so on, by, let's say, traveling back and forth to the facilities of the lending party or of the letting party. This is where cloud computing provides the convenience factor. The cloud computing service provider would have hosted these services in their own facilities, and they offer these services to the end user over the internet in a self-service provisioning model. So the service provider would extend a self-service provisioning capability to the tenant, where the tenant just needs to go into the, let's say, the self-service portal, okay, which is maybe a website, log in or sign up with their credit card or bank information, create their own account, user ID and password, and start using the services. So if I want to create a virtual machine, I would go into the dashboard, that is, say, in terms of OpenStack, we would call it the Horizon dashboard. I would go into the web-based interface, log in, and create a virtual machine myself. Okay, so if I require a machine with, say, 4 processor cores and 8 GB of RAM, the OpenStack cloud, or however it has been built by the service provider, would give me the capability to create that server by my own self. I have the advantage of self-service provisioning, and I have the advantage of pay-as-you-go billing. That is, I pay for only the hours that I will use that server. So these are two of the benefits that cloud computing offers to us. Cloud computing, a platform or the environment, is a multi-tenant environment. That means the same services are offered to multiple users by the service provider or multiple tenants by the service provider, and the service provider reaps the benefit of massive scale business, economies of scale. They are able to provide the services to the consumers or the tenants at a much lower price or a very reasonable price, and they're able to still make profit by offering it to different users at once. So cloud computing also provides on-demand and rapid provisioning capability. So we can create the servers when we need them. We need not make any upfront investment, and we pay only for the time that we have consumed that service. So if my server has been running for 2 hours, I'd be billed for 2 hours, and I can deprovision it, that is, delete it as and when I see fit. So if my job is done, if the work for which I had provisioned the server is done, I will be able to delete the server and do not incur any further charges. Okay, so these are a few benefits that we derive from a cloud computing model. And OpenStack is one such tool that helps us build this kind of a platform. So when I say us in this context, I mean the service provider. So we may want to build a cloud computing platform for our own organization, or we may want to build a cloud computing platform to offer the services to the general public. And this is where OpenStack comes in. OpenStack gives us the tools necessary to build this cloud computing platform and host these services that we are going to offer either to the general public or to our own users in the company. Okay, so OpenStack, as we said, it's a set of tools, set of software tools for building and managing computing platforms. And OpenStack project or the open source OpenStack development effort is managed by the OpenStack Foundation that oversees the development, oversees the strategy, the approach required to take the development of OpenStack further. So it is an open source effort. However, a lot of large companies, a lot of large enterprises are contributing to the development of OpenStack by means of source code, by means of contributions, and so on, as well as they are adopting OpenStack to align with their own product strategies. So here are some companies listed who contribute to OpenStack majorly. So OpenStack itself consists of many different services which take care of different aspects of the cloud computing. So here we can see some services listed and the relationships between them. So we have to remember the end goal, which is to offer infrastructure as a service to our consumers. So now this point onwards, we can assume the role of a service provider, or we can assume the role of, say, we will assume the role of the service provider who builds the cloud computing platform and offers the services to its tenants. So we want to build an OpenStack cloud and offer infrastructure as a service to our end users. And by infrastructure as a service, we mean services like virtual machines, services like storage volumes, object storage buckets, virtual networks, and other services that go along with it, like Ceilometer, which is for monitoring, Keystone for authentication and authorization. So in our OpenStack cloud, if we need the capability to host a virtual machine, then we need the Nova service. The OpenStack Nova service takes care of managing virtual machines in the OpenStack cloud. Similarly, the Glance service is a helper service to Nova, which takes care of managing the virtual machine images which are used by Nova to bring up the virtual machines. The Swift service hosts the object storage capability. Object storage is a modern distributed storage system that provides massively scalable and durable storage. That means we can grow the storage capacity to a very large level and we can store our data in a durable configuration. There is very less chance of losing the data. If by storing our data on the storage system provided by Swift, we can ensure that our data remains durable. That is, we do not lose the data, even if there are failures of different devices. That's what we mean by durability. And Neutron, again, is another, we can say, service related to Nova. Neutron provides the virtual networking capability necessary to connect our Nova VMs or Nova instances to a network. So without Neutron, it may not be possible for Nova instances to connect to a network. And by definition, the cloud service is remote. That is, if we create a server using Nova, the server is hosted in the service provider's infrastructure and it needs to be accessed by the consumer from a remote location. Okay? The remote location could be another continent entirely, or it could be just another office in the same city, or it could be another building in the same office, and so on. However the case may be, however far the consumer may be, they still need to connect to the resources or to the Nova instance over a network. So Neutron is very, very essential in this case in order to provide networking capability for our Nova instances. Similarly, with the Cinder service, we are able to create block storage volumes for use with the Nova virtual machines. So Nova virtual machines, as the name suggests, they are actually virtual computers. And like any other computer, the virtual computer will also require storage capacity to hold the cold data or to hold data at rest. So we need to provide, let's say, a virtual disk to a Nova instance so that it can store the data necessary to run the virtual machine. So say in your laptop or in your desktop, you have a hard disk which holds the files necessary to run the machine or to run the operating system. Same way, for a Nova instance, you require a storage space to hold the files for the operating system as well as any user data. So anything that the user would store, like a database or image files and so on. So you require a lot of storage space if you are hosting a production level application. In a production level application, the data may grow to massive levels. So you require the virtual disk functionality to add a virtual disk to a Nova instance, and Cinder provides us that. Okay. Heat and Ceilometer are not directly related, but they provide additional capability in our cloud computing environment by, let's say, facilitating monitoring. Ceilometer would facilitate metering and monitoring, and the heat service would facilitate orchestration. I'll explain more on that once I get to those slides. Okay, so the Horizon service I did not touch upon in the last slide. The Horizon service is a web GUI or graphical user interface for anybody to interact with the OpenStack cloud, be it administrators or be it end users. They would interact with the OpenStack cloud, that is, they would create resources like Nova instances on the cloud by using the Horizon GUI. There are other methods as well, like the command line interface tools and application programming interface calls. So I think I have a OpenStack environment running. I'll show you an example of each of these services. Okay, so in this case, my OpenStack is running locally on this address, so I should be able to access the Horizon dashboard. So as I've just mentioned, Horizon is the OpenStack's dashboard service, which provides a web-based user interface to OpenStack services, including Nova, Swift, Keystone, etc. So basically, it's a way for users and administrators to interact with and manage the various functional components without having to install any local client tools other than a web browser, as well as providing a self-service management tool or self-service console for the end users. So in one of the benefits of the cloud computing, we had mentioned that cloud computing provides us self-service provisioning capability. The self-service provisioning capability is realized using the Horizon dashboard, and it gives intuitive user interface for, say, non-technical users as well as technical users to create resources or create services from the OpenStack offerings. So as a service provider, we would offer certain services to the end users. And the end user will be able to pick from those service offerings and provision one for themselves. So in this case, if the service offering is a Nova instance, then the user will be able to select that service offering and create an instance. I'll try and show you an example. Okay, I think there's something wrong here. Just a sec. Okay, so there has been a change into the configuration. I'll just fix it quickly. Okay, now we should be able to access the dashboard. Okay, while that loads, we'll try and move on to the next service. So Horizon is kind of the service that keeps or gives us an entry point into our OpenStack cloud. All the other services that we see so far do not have a direct interface with the users, at least from the graphical interface point of view. Most of these other services have a command line interface. So for administrators and for technically sound users, it's possible for them to interact with these services using the command line interface. Okay, so this is how the dashboard looks like. So one of the very important services of OpenStack is Keystone, which provides authentication and authorization services for our entire OpenStack environment. So if I have to provision a server on Nova, if I have to create an instance on Nova, then I as a user would need to make an authenticated call to the Nova API. And the responsibility of authenticating and authorizing my API call would fall on Keystone. So it does a little more than that as well. So OpenStack Service Keystone provides API client authentication, service discovery, and distributed multi-tenant authorization by implementing the OpenStack's identity API. So Keystone, we can say, is similar to your Active Directory, only it operates or it extends that functionality to the other OpenStack services. So here, if I enter my username and password in the OpenStack dashboard, the dashboard service, which is Horizon, will also contact Keystone to authenticate my details, to validate the credentials. So Keystone would hold a list of users that are authorized to use OpenStack or that exist in the OpenStack environment. It will also hold a list of services. So list of services would include what services are on offer from this OpenStack cloud. Okay, let's quickly check if the login has succeeded. It has. So I'm logged in as the admin user. So this is where I manage the users, groups, and projects. And at the back end, this will affect the Keystone details or the Keystone database. So Keystone is the service responsible for holding and managing these things, like these users. Okay, users like admin demo, and these are service users for each of this service. So all of this information is hosted in Keystone. Okay, and if we do a OpenStack project list, it will take a couple of minutes because the environment is running on a virtual machine. We will be able to figure out all the projects that's listed here. Okay, so this is the graphical user interface, and we can accomplish the same task using the command line, like here, service admin and demo. For the service project, the ID ends with 682, same 682 there. Okay, so Keystone would hold these details, and when I say OpenStack project list, it actually queries the Keystone database and brings up these details to show to the user. So at this point, I am the user. I'm logged in as admin. I can view these details because Keystone is functioning. So from the projects page, the project section is the one which is visible to a general user. The admin user can see all the admin capabilities as well. The general user would only see the capabilities that are provided to him, provided to the user, him or her. And this is the service catalog or the service discovery that we are referring to in the slide. Okay. And again, this is hosted by Keystone. So Keystone is telling us where each service is. So how to contact, say, the Keystone service itself, how to contact the database service, how to contact the volume, which is Cinder service. Volume and volume V2 belong to Cinder. Alarming belongs to Ceilometer. Compute belongs to Nova. CloudFormation belongs to the heat service, basically. Orchestration and CloudFormation belong to the heat service. Image is the endpoint for glance service. Okay. So we have all these services installed in our OpenStack cloud. And by querying the Keystone API, we can list the services which are available. So this is how Keystone acts as a service discovery tool as well. Okay, so the same thing I can get by running OpenStack, say endpoint list. So Keystone, in a nutshell, will provide authentication and authorization services for different other OpenStack services like Glance, Nova, and so on. Keystone is used for authentication into OpenStack Horizon. Keystone supports token-based and user service authorization. So Keystone basically associates a token with each user session, and using that token, the user can make API calls, validated API calls. So you see I did an endpoint list here and it's showing me the endpoints. Okay, so if I say OpenStack token issue, this is the ID, this long string that you see is the ID of the token that OpenStack has given us. And I can pass this token ID along with any other API calls that I make, or maybe my application makes for authentication and authorization purposes. So by looking at this token, Keystone would know that this request is originated by a particular user mentioned in this user ID, and the user belongs to a certain tenant. So even while logging on to the dashboard, OpenStack Keystone comes into the picture. The Glance project provides a service where users can upload and discover data assets that are meant to be used with other services. So basically, Glance project would provide hosting capability for virtual machine images. This currently includes images and metadata definitions. So you would mostly be using the Glance service for virtual machine images. Virtual machine images are, let's say, pre-configured templates for use with Nova instances. So in a traditional environment, or in a environment where administrators have direct access to the machinery, they install the OS separately. So you have a desktop or a laptop. If it is new, it may or may not come with the operating system. When it does not come with the operating system, you have to, say, insert a DVD or a USB stick with the OS image on it and install it manually. However, that procedure or that approach is not very user-friendly when it comes to the cloud computing environment, because we need to rapidly provision resources. So in the cloud computing environment, we would have pre-configured virtual machine images that we would use to bring up Nova instances. So if you take a look here, say OpenStack image list, and if you take a look at the dashboard as well, we can see that right now there are two images. One is a Cirrus. The name of the image is Cirrus. The uploader can name it anything they like. It should be descriptive. So it should describe what is contained in that image. So I have named it Cirrus, and I know that inside this image, I have the operating system files for the Cirrus operating system, which is basically a very lightweight Linux operating system. Same way in the MySQL test, it is a Trove image. Image for the database service, and it contains an installation of MySQL on top of one Linux flavor, maybe Ubuntu or it may be CentOS. Basically has the OS as well as the SQL database installed on it. So you see the same output here as well. So these images will be used by the Nova service to bring up an instance. Okay, like you see here, there's an instance 01, which was brought up using the Cirrus image. It's shut off because my entire virtual machine was shut off. I can start it. So while launching an instance, we have to specify the image ID of the Glance image. So even before you can create a virtual machine, you have to upload the image to Glance. And we can launch a virtual machine in different ways. One of them being from Horizon. The other one, you can just run a command, say Nova boot. So with the Nova boot command, we can start an instance and specify the flavor as well as the image, security groups, NIC card, the name of the instance. Okay, this is instance 01, which will be running in a bit. And to the end user, this instance 01 will mean something like a web server or a application server or a DB server. So the Glance service will be responsible for maintaining these images and providing them to Nova as and when necessary. Something like this. So as I mentioned earlier, Nova is like the mainstay of the OpenStack Cloud. It does the heavy lifting of creating and managing the virtual machines that a user could provision on the OpenStack Cloud. So it is designed to be massively scalable, and it is designed to be distributable. So we can have multiple compute nodes running together in our OpenStack environment, and all these compute nodes will be hosting virtual machines based on user demands. So it is possible for us to add more compute nodes and add to the capacity of our OpenStack Cloud. So the Nova Compute service is basically responsible for interacting with the hypervisor and bringing up the virtual machine. Other services like Nova API plays the front-end role for the Nova service. So when in Horizon you click launch an instance, it would contact the Nova API and bring up the instance. So Nova API would take care of the rest of the of initiating the rest of the procedure. It will first verify that the request has originated from a valid user. Then it will create a database entry and pass on the request to Nova Scheduler to take it further. So Nova API is also compatible with Amazon EC2 API. So any application which is written to work with Amazon EC2 can be directly used with the Nova service. So the Nova service collectively is comprised of these different services like Nova API, Scheduler, Conductor, and Nova Compute. All of them have a designated function, and their collective goal is to provide hosting capability of virtual machines on the OpenStack Cloud. You can see that on the dashboard by looking at instances. Okay. When we say launch instance, we have to provide details such as instance name. We have to provide a name with which the instance will be launched. Let's say instance 10, select an availability zone and say how many instances are necessary. And we have to provide the image ID here. So we have to provide these details in order to launch the instance. And once we are done providing all this, Nova Scheduler, Nova API, and Nova Scheduler, and all other helper services will take care of bringing up this instance just like this one. Okay, this instance is up and running. It was created 3 weeks earlier, and we just powered it on again. Okay, and you can see that this is just a server or a virtual machine running on resources that the service provider has arranged for. And it can be used by the end user, let's say me at this point, to host any other service that I would like. So if I need to use it as a web server, I'd install a web server component like Apache and make it a web server. So a screenshot of the OpenStack dashboard is shown here. And you could list the instances from the command line by OpenStack server list. Okay, while that works out, let's move on to the next service, which is Neutron. Neutron is a networking project focused on delivering networking as a service in virtual compute environments. So initially Neutron was called Quantum. It's been renamed and it has been improved massively. So in a cloud computing environment, it's necessary to have a software-defined networking component so that we can extend the functionality of creating virtual networks to the end users. And Neutron gives us that exact same capability, us as in the service provider, to run the Neutron service and offer virtual networking capability to the end user. So something like this. You can see that in the network tab. Go to networks. Here you see that we have created 2 external networks and 1 internal network. So external networks are mostly created by admin users, and they are made available to the other users, to the general users. General users are free to create their own private internal networks. So this internal network will be valid only in the OpenStack Cloud. So any instances that the user creates can be attached to this network. So you can see that our instance, one of the instances, has an internal IP address belonging to this particular network. Okay, so this one is 172.16.0.11. That means the private IP address of this instance is 172.16.0.11. This is the floating IP, which is basically an external IP from the external network. Floating IP can be attached to any of the instances for us to access them from the outside. So in a production environment, the floating IP could be a public IP address. Because this is a lab environment, we have associated public or private IPs as the floating. So using the floating IP, I should be able to access it from my desktop if it still works. I'm not quite sure. So the Neutron functionality visible on the dashboard from the network tab. You can create networks here, you can create routers here. And if you want to visualize your network topology, you can go to the network topology tab. This is basically a visual tool that OpenStack has come up with. This is admin router 1, this is the external network, and this is the internal network. The two instances, the MySQL instance and instance 01, they are connected to the internal network, and they are connected to the external network via the router. So if there is no router attached connecting the internal network with the external network, then it's not possible for us to attach a floating IP. So it's not working, I guess. I'll try to ping the external IP of the router. No, I think there's some problem with our configuration. So we'll get back to that later. Okay, so Neutron will provide us this capability of creating networks. This is external network 2, which I had defined in order to test something. We can create different internal networks based on our necessity, and each tenant can create their own internal networks if they so wish. And it is the function, or it is the job of Neutron to facilitate this capability to the end user. So moving away from the compute service for a bit, we can talk about Swift, which is a storage system, or more precisely, it's an object storage system. And it provides us the capability to host a storage service that stores the data, that stores the object in a very, very durable form and in a highly available configuration. So the Swift service helps us achieve that. The Swift service helps us configure the underlying resources like storage disks, storage nodes, proxy nodes, and so on, so that they can host this service and provide the users the capability to store their data in a highly available, distributed, and eventually consistent model. Okay, so the workflow is somewhat like this. The user application uses Keystone for authentication and accesses the Swift proxy to get or put object. So in order for us to understand Swift in more detail, we need to brush up on the object storage system and find out what benefit it provides over, say, traditional storage system like file or block storage. Then we will be able to appreciate the capabilities of Swift. For now, we can assume that it provides us a very durable storage capacity or storage system. So the Swift options will be available under the Object Store tab in the containers. A container is a virtual storage folder, or so it says a container is a storage compartment for your data. It provides a way for you to organize your data. You can think of a container as a folder in Windows or a directory in Unix. The primary difference between a container and these other file system concepts is that containers cannot be nested. You can, however, create an unlimited number of containers within your account. Data must be stored in a container, so must have at least one container defined in your account. So you can say, let's say for application 1. So I can use this to store all the data related to application 1. Okay, container application 1 created. At this point, there are no items here, so I can upload a file, say choose file. Okay, let's say this index.html and upload. The other advantage of object storage system like Swift is that it provides us a direct HTTP based link for the objects. So the index.html is here. I can access it. If it is public, it's a application1 index.html. Okay, so controller name is not recognized here. I need to replace it with the IP address. Okay, and well, it's not hosted using Amazon S3, but it's just an example. So we can host unlimited amounts of data based on the backend storage capacity in Swift. Okay, next is the Cinder service, which provides us block storage capability for our OpenStack instances. Okay, that is available in the compute in the volume section. So if we need an additional hard disk for one of our virtual machines, we can create it using Cinder. Cinder provides persistent storage. That means if we do not use a Cinder volume, then the data on our virtual machine is lost when we delete the virtual machine. And there's no way for us to keep that data except for copying it over the network. So before deleting the instance, if we copy the data over the network, we can keep it somewhere else. But with the Cinder service, the Cinder volumes can be kept independent of the life cycle of your EC2 or of your Nova instance, and can be installed or can be attached later on with another instance to recover the data. So in the event of a failure of a EC2 instance or a failure of a Nova instance, we can still keep our data and access it again from a different instance by attaching the volume to a different instance. Okay, that's why it's mentioned here that it provides us persistent block storage resources. It's persistent in the sense that the data is not lost when the instance is shut down or rebooted or deleted, provided that the settings are correct. So this includes secondary attached storage similar to EBS, of course. So we can attach multiple volumes to a single Nova instance and keep, say, the data disk separate from the operating system disk. Okay, so the Cinder service, again, the name is a collective name for different helper services that run and provide us this capability. Moving on, the Ceilometer service basically provides us, okay, so there's a screenshot of the volume list. We can create volumes and attach them to the Nova instances. The Ceilometer service provides metering service basically for the OpenStack resources. So as discussed in the very beginning of this presentation, any cloud operating or any cloud computing environment has to do a metering and chargeback in order to provide the user with a pay-as-you-go capability. So the same thing, at least the metering part, is done using the Ceilometer service, as well as to some extent monitoring. So Ceilometer service is capable of capturing metrics related to the services that the user provisions, like a Nova instance or a load balancer or something. And based on the captured metrics, the Ceilometer's alarm service can raise an alarm if necessary. Otherwise, it will provide user usage details. And at this point, the Ceilometer service is only available for the administrator users. So we have to look at in the admin tab and go to the resource usage. And Ceilometer would provide us a graphical representation of the usage data that it has been metering. Okay, so when that comes up, we'll take a look. Finally, Heat is one of the add-on services that we can have in our environment. It provides us orchestration service, that is basically to launch multiple composite cloud applications based on templates in the form of text files that can be treated like code. So it's a way of creating repeatable infrastructure. So if I am a developer and I need a certain app environment, let's say I need an environment of 3 servers, one of them is a DB, another one is an app, middleware, and one of them is a web server. And if I need to keep testing my code again and again by creating that environment every time I test, then I can use something like the Heat service to define that environment in a template. In the template, I will define it as text and use the Heat service to bring up all the resources that are defined in that template. And I can create or destroy the stack of resources as and when I need them. Okay, so we can see there's an image size, all these meters are there. So it should give us some representation. So here it is, close to 250 MB, I believe. Okay, so all these services need to be installed in your OpenStack environment and configured. And the place where you install these services, we can call them the management infrastructure. Okay, so you will have management infrastructure and the managed infrastructure. So in this case, if you take the example of Nova, then the management infrastructure will be the ones which are running the Nova services like API, Nova Scheduler, and so on. And the managed infrastructure will be, say, the compute nodes. Same goes with same goes with Swift and Cinder. In that, the managed infrastructure will be the storage nodes. The management infrastructure will be the servers which are running, say, the Swift proxy service or the Cinder API service. So it's always advisable to keep the managed infrastructure and the management infrastructure separate so that there is no contention of resources between both. The managed infrastructure will always host user workloads, and the management infrastructure will always host the services that run our OpenStack cloud. So usually OpenStack is installed on Linux distributions or Linux operating systems. And there are several guides available for installation on different Linux distributions like Ubuntu, CentOS, and so on. Now there have been multiple success stories as well as multiple examples of when, say, different companies have operated OpenStack clouds to their advantage. PayPal is one such company, which is a worldwide leader in online payment system. PayPal runs 4,100 standardized x86 servers under OpenStack to provide 162 million customers with information, mobile application support, website interactions, and payment processing. So the requirement was to design an architecture to reduce the current wait time of about 3 hours for the developers building development hosts at PayPal. The requirement is to process huge amount of data, reduce wait time, real-time resource allocation, and faster development. So with OpenStack, it was possible to achieve all of that. OpenStack Cinder was used to clone the data in the file system, and it avoided nearly all the network I/O of booting an image. PayPal moved from booting up new images from glance to using Cinder to clone VMs using Flyway. PayPal thus could rapidly deploy a staging environment in just 14 minutes. So Flyway is the PayPal solution tool for migrating cloud resources. It is responsible for migrating thousands of VMs from eBay to PayPal. So PayPal has implemented OpenStack by using 100% KVM hypervisor. It has 12,000 plus hypervisors and 300,000 plus processor cores. And the entire networking is supported by Open vSwitch. Okay, so to summarize what we've seen, we had an introduction to OpenStack, we had an introduction to the OpenStack architecture, briefly went through each of the OpenStack components and learned what each component does. Okay, remember that these components are part of the management infrastructure. And so the functionality that is exposed to the end user depends on the components that you have installed in your OpenStack environment. So eBay was the parent company of PayPal, and we saw how eBay or PayPal migrated itself away from the eBay infrastructure by using OpenStack. And they have used it at a large scale, which proves the reliability and the robustness of the OpenStack platform. Through the Edureka OpenStack certification training, you would be taking a first step into learning cloud building tools like OpenStack and gain general overall knowledge about cloud computing platform as well as OpenStack. So that is the end of our presentation today. If you have any questions, please let us know. Otherwise, we can wrap it up here. Thank you very much for joining this session.
I hope you enjoyed listening to this video. Please be kind enough to like it, and you can comment any of your doubts and queries, and we will reply to them at the earliest. Do look out for more videos in our playlist and subscribe to our Edureka channel to learn more. Happy learning!